Okay. So today we're going to start on multi-level models. We've been building up to this for a while, and I think this is I'm a bit ridiculous about this, but this is a unit that I have been excited to teach, and one of the reasons I was really excited to kind of move the course over to this book because it kind of builds up toward this. And the Bayesian approach really fits nicely within a multi-level framework. A multi-level modeling framework in a frequentist approach is really useful, but it's a kind of pseudo-Bayesian approach there, right? And so it's nice to just kind of go fully all the way. And so once we learn multi-level models in this framework, you'll have an easy job extending it into a frequentist framework if that's what you'd like to do, because the logic of it really is in any framework, it's a sort of pseudo-Bayesian approach. What we're going to do is we're going to add parameters to the model to add complexity for different clusters. So given our kind of, you know, the manual way that we've been specifying models and the way that we've been really careful about thinking through what our parameters are, this shouldn't be too hard for us to grasp. It can be a little tricky if you haven't been thinking in this way. But without further ado, let's dive in. So, just a reminder, we're going to spend this week um, introducing multi-level models. We'll be diving in further next week and also in the following week. So the remainder of the class is really going to be focused on multi-level modeling. So we have a few weeks to get our heads around this. So first, let's talk about what we mean when we say multi-level data. Sometimes, I'm going to use the generic term multi-level. Sometimes you'll hear people use the term hierarchical is another way to talk about this. Multi-level data is often hierarchical, but it's not always hierarchical, right? You might, see some context where we have levels that are not necessarily kind of strata where one group is nested within another group. But multi-level is a very broad framework for thinking about data that has clusters to it. So a lot of natural and social processes have some kind of inherent grouping. They, for example, organisms live within ecosystems, right? We were looking at salamanders for the homework, right? Or fishing results within a particular park, right? So the structure of the counts of animals living within a place is very much a feature of the place that it's in, right? And if we have comparisons across different ecosystems, the ecosystem itself may play an important role in structuring the count of animals within a place, both because of things that we've measured about the place and things that we haven't measured about the place. People live within neighborhoods, right? And so there's been a ton of research looking at how social mobility is a function of where people live, right? If you think of the Raj-Chetty research or a variety of research in demography and in sociology on social mobility, Robert Sampson's neighborhood effects research in criminology, we have profound amount of literature that shows that the neighborhood you live in has a dramatic effect on your behavior and on your life chances. And so the neighborhood you live in is a sort of cluster that a group of people all experience similar outcomes within, right? And of course, those neighborhoods are nested within cities, right? So the neighborhood could matter you're in, the neighborhood you're in could matter, but the city you're in could also matter, maybe in a different way, right? And so these kind of groupings, these clusters can structure the outcomes we're looking at. An obvious one within education research is that students learn within classrooms, right? And so we could think about the not just your test scores if you're a student could be a function of the teacher that you're exposed to. And the performance of that teacher or the performance of that classroom could be a function of the school that they're in, which could be a function of the district that they're in, right? Which could be a function of the state that it's in. And so all of those levels can influence what's happening to our data. And a multi-level model is a really convenient way for us to capture all these differences. So these groups, right, these kind of hierarchical, in that case, all the examples I gave were hierarchical structures, right? That we have a kind of nesting of an organism within an ecosystem, a smaller unit within a larger unit, people within a neighborhood, a person within a neighborhood within a city, student within a classroom within a school within a district, right? These groupings often lead to a pattern called clustering, right? Where we might see a set of observations that are similar on some set of predictors or some set of outcomes, right? That we see correlations that are strictly due to the fact that they exist within the same unit. So these variables are often highly correlated with each other. And these correlations could be a function of observables that we have. For example, it could be that in the neighborhood effects literature for criminal behavior, right? Collective efficacy within the neighborhood is often found to be the explaining feature of why neighborhoods matter, right? And so that could be something we can observe. We could go out and measure collective efficacy and say, okay, we can explain the variance within this cross clusters as a function of collective efficacy. But it could also be due to unobserved or unobservable features of the cluster, right? Where it could just be that this neighborhood has higher levels of vandalism than this other neighborhood in a way that none of the observed variables that we've got can really account for. And the multi-level model can help us account for those unobservable features, right? If we don't account for clustering, our inferences will often be misleading, right? That these kind of sources of unobserved variation across clusters, right? So if we have observed variables that can explain out the cluster variation, then we can get unbiased inferences. But if there are unobserved features of the data, which there almost always are, that are driving some of the correlation within a cluster, if we don't account for that clustering, the inferences we obtain will not be reliable. So clustering is something we need to account for explicitly. Another source of structure we often see in the data is repeat measurement of the same unit over time, right? That's kind of a longitudinal data structure where, for example, we might measure the performance of a single student over time to look at the trajectory of growth on, for example, their reading performance, right? We might want to know how much the student is improving in their ability to read. And so we might measure them each year. Now, obviously, the individual is a pretty clear cluster there, right? The scores in time 2 very much depend on their scores in time 1, right? And their scores in time 3 depend on their scores in time 1 and time 2. So we need some way to account for the fact that this individual has scores that are going to be correlated with each other, right? And a multi-level model is a really nice framework to do that with. So we're going to kind of broadly introduce the motivation for multi-level modeling, and then we'll get into the nitty-gritty of how we actually build these things. So I'm going to start by using the Gapminder data. So if you don't have the package installed, you can install it with install packages, Gapminder. And what this is it's a variety of UN data on life expectancy, on population size, and on GDP across countries over time. So it's got data every 5 years on life expectancy, population, and GDP for every nation in the world. Now, we have some differences in the number of units observed because some countries can't. This data starts in 1950, and some countries come into being between 1950 and 2012, right? So not only do we have repeated measurements of the same country over time, but we have different numbers of measurements for each country, right? So our precision might differ across countries because we have more information about some countries than others. Okay, so let's say we want to learn something about average mortality rates within countries. We're going to start with the simplest model that I can imagine, which is a normal likelihood model for life expectancy, right? We're going to model this column, life x, right? I'm going to turn it into just a variable named L for now. So we're going to model this. It's continuous and it's, relatively high. So I think a normal likelihood is fine for this. We're not going to, if we use reasonable priors, we're not going to sample negative numbers. So I think a normal likelihood will be fine. I'm going to use a single parameter to start. That's alpha, right? So I'm going to say that a country's mortality is a function of a single intercept alpha. And we're going to let alpha have a normal distribution with a mean of 55 as a prior and a standard deviation of 15. And where did I come up with this? I kind of pulled it out of thin air, but I was thinking, what do I think are reasonable values for life expectancy? Well, 55 plus 2 standard deviations, if my standard deviation is 15, gets me up to 85, which I know is higher than any country's current life expectancy. And 55 minus 30 is 25, which is really low, right? So that covers, I think, the plausible values for what life expectancy on average in a country could be. I'm going to use an exponential for sigma as we've been doing. Notice here I'm using a 0.5 instead of the 1 we've been using. Now, lower values on the rate parameter for an exponential distribution actually fatten the tails, right? So a 1 does not have much probability mass after sigma equals about 5. But in this case, because the scale of my variable is higher, right? The expected value for my prior is 55. I want to allow more variance than an exponential 1 would on the prior. So a 0.5 allows prior plausibility for like a standard deviation of 10 to have some plausibility on it. And that's what I want. So if you think you have a high possible value for sigma in a normal likelihood, use a lower value for your exponential prior, right? And when I was building this, I toyed around with exponentials of 0.2, right? And I think those are fine here as well. So 0.5 is what I'm going to stick with for my prior there. Okay, so it has no included parameters for group differences. This is called a complete pooling model, right? I'm pooling information from every country, and I'm generating a single estimate for my regression prediction, right? I'm pooling all of the data. So we're going to discuss 3 models: the complete pooling model, the no pooling model, and the partial pooling model. So this is the complete pooling model, right? I'm not paying attention to differences across units at all. I'm pooling all of the data to make my inference. So this is how I estimate the model, right? I'm going to turn country into a factor because I'm going to use that later. But this is the similar model that we've been estimating for quite a while now. Any questions on the specification here or here? We feel good about this? 3, 2, 1, go. Okay, cool. So I'm going to visualize it same way I've been visualizing things for a while now, where I want to generate a prediction for every country in the data, right? So I'm going to make country a vector where I get 1 entry in my data frame for each country in the data. And I'm going to predict for each of those countries, right? And just take the PI and then get myself a nice ribbon. And I'm going to arrange here so that the smallest country appears on the left side and the lowest life expectancy. So we get a sort of sequential order. It'll make the plot easier to read. Okay, here's what we get. The red is my model predictions. It's the MAP estimate for the model. What's going on? We only gave a single parameter for alpha here, right? So does the model have any way to predict different values for each country? No, the model's guess is going to be the same for every single country. And this will minimize error across all countries, but it's going to mean we predict the exact same value for every single country. Our expected value is the same everywhere, right? And so, at the average, we have minimal error, but out for the high and low life expectancy countries, we have quite a bit of error, right? So this model dramatically underfits the data, right? There are features of the data that we could have learned from that we did not learn from when we use this complete pooling approach, right? Now, it is relatively precise in the posterior, right? Our alpha is 59.46, and our standard, our interval here is pretty tight, around 59, right? So the model's really sure alpha equals 59. But what happened here is this complete pooling intercept-only model, right? Effectively, what it did is it told the model what you should do is you should guess the average value for each country, right? That's going to be in the Gaussian likelihood, right? That's going to be the best guess that's going to minimize error. And so what we see here is the empirical mean of the data for life expectancy is 59.47, and our estimate in the posterior for alpha is 59.469. right? Those are indistinguishable from each other. So in the case of a complete pooling model where we're using intercepts, what it's going to do is it's going to take the empirical mean for the full data, and that's going to become our intercept term. We're going to see that this is going to extend to other approaches as well, right? We need to think of intercepts as means. Intercepts are group means. And in this case, our group is the full data. Questions about that? And when we estimate this intercept-only complete pooling model, the alpha we get back is just the group mean for the full data.
So, so does that mean that the model basically is very good at predicting central tendencies, but will be poor at the edges?
No, I mean, kind of. This predicts well at the center of the distribution. It predicts poorly everywhere else. Um, it means we have a lot of certainty about what the average is in the data because we have a couple hundred rows. That's all it means. But I want you to think about when we're estimating. Obviously, this is a pretty ridiculous example, but when we're estimating, for example, intercepts for different groups, right? As we'll see next, if there are clusters within the groups that we aren't accounting for example, if we put in a predictor for each continent, right, as a dummy variable, that will improve our fit. But effectively, those alpha parameters for each continent would be the within continent average, right? And then it would just predict the same value for each continent. So I just want us to start thinking about intercepts as means. I don't want us to think too hard about using this model because it's obviously a poor model, right? But I want us to kind of internalize that the intercept is just a mean, right? It's just a mean for whichever larger group that we've specified in our model. Okay, any other questions about this? Okay.
I guess
Yeah.
I'm just a little confused as to why it's called complete pooling.
Mm-hmm.
Like, is there any statistical significance to the pooling portion that we should understand? Because to me, it's just like this is a simple model with one variable.
Yeah, the pooling kind of idea is that we are going to build out a set of models that are better or worse at sharing information across groups, right?
Okay.
So in the complete pooling approach, we share information across all groups in the data without specifying any within group differences at all. So maybe the pooling idea will become more obvious when I move to the no pooling model.
Okay, thank you.
So in this, we're estimating the expected value of the data based on the full data without making any distinctions across units. But next, we're going to move over to the so when to avoid complete pooling. So sometimes units in the data have features that make them similar to other units, right? Like maybe we have repeated observations of countries over time, as we have here, right? That's called longitudinal or time series data, right? So in this case, we have what I would call a time series, where we measure countries over time, right? And this is a really common format for data in the social sciences, right? Where we have, or in the natural sciences too, if we're looking at sensor data or something like that, where we have measurements of the same person, place over time. So those repeated observations give them structure, right? And so ignoring that is ignoring a really important source of variance in the data. We could also have observations of many countries from the same time period, right? So we could have longitudinal data where we have one country over time, or we could have a lot of units observed at the same time. That's called cross-sectional data, right? Where we have a constant, and that constant is time, and then we observe a lot of units at the same time. Now, the Gapminder data is a special merger of time series and cross-sectional data that gets called time series cross-section data or panel data, right? Where we have the same set of units observed over time. So effectively what we have is n longitudinal data sets where n is the number of units we've observed, right? But we also have other structures here, right? Countries are nested within larger geographies, regions, continents, regions again. Uh, yep, there we go. We can adjust our models to learn from these features and to improve inference, right? So we can actually bake these features of the structure into the model. So next, let's move over to kind of walk through
I
some
have
of
a
the,
quick question.
yeah.
Sorry. Is panel data from the previous side, is panel data always longitudinal data?
Yeah, panel data is always longitudinal, but it's longitudinal over many units, and those units are often the same.
Okay. Thank
Right.
you.
So in panel data, you don't necessarily always have the same number of observations for each unit, but you have a consistent set of units, right? So if you ever hear someone say a balanced panel, it means you have n observations of k units where n and k are fixed. So that means, maybe I have like 12 observations of 20 units, and I've got 12 observations for every of those 20 units.
On any of the okay.
Yeah.
Okay. Okay.
Unbalanced panel would mean that I have a fixed number of units, but they drop in and drop out. So I might have like 5 observations on one unit, 12 on another, 25 on another, 2 on another. That's
At different time periods.
yeah. They might
Okay.
be at the same time period, but they might like drop in and out of the data.
Okay.
Yeah. So panel is something we see a lot, right? And something I work with a lot. And they have a special structure that really does require some care when thinking about how to model it. Okay, so the no pooling approach is obviously not great, right? Because, hey, why did we even bother with a model? I should just say, I guess the mean, right? And that's the least wrong answer that you could get, if you're just going to give a single number for the full data. But we could do better than that. Any other questions? This stuff is hard, so please do slow me down and ask questions.
That's one question I have. And I know that we're only working with intercepts here, but in the homework it talked about hours versus like days. Is there a way you can like adjust time, or maybe I'm just
The homework. So you're thinking about homework that we just completed?
Yes.
That was an offset. That wasn't
Right.
really a cluster. Um,
Okay. Right.
you could imagine potentially like groups with kids and groups without kids being kind of different kinds of clusters if we think about these as categorically different groups of campers, right? I could imagine a multi-level model for that, but no, that's not really a clustering variable. That's an exposure variable. That's a like
Okay.
how
That
much
was
time was there for the event to occur.
Okay. I was just thinking maybe in like terms of life expectancy, you might see that as well. Like I don't know. So, but that's kind of in the weeds. So.
Okay. Yeah, and I noted your. I'm sorry, I missed your question on Slack. I did post the solutions for that homework question. Sorry, I've been a bit delayed on getting homework solutions up. Yeah, things time has been constrained lately. Okay, so other questions on the complete pooling model or this idea of clustering? No. Okay. So this is kind of what it looks like with complete pooling and why we might start to think that it's not a great idea, right? Now, if we had just a simple normal curve, say this shape, guessing alpha with a standard deviation around it wouldn't be too bad, right? Because we can effectively predict out a normal distribution with just a mean and variance. But this clearly doesn't take the shape of a simple normal distribution, right? It looks like we have a mixture of normal distributions here. We have some group of low life expectancy countries, kind of one mode here. We have another little mode here, kind of mid-range life expectancy countries, and then a large peak here with high life expectancy countries, right? So here, this isn't a simple distribution where we could say, you know what, we could probably guess accurately with a single mean and variance parameter. Doesn't look like we're going to be able to do that here.
I have a question.
Yeah.
Is clustering sort of similar to like multicollinearity in a sense, in that there's like different like distributions within the data? Does that make sense?
Yeah, so I think of multicollinearity as a problem really specific to linear regression, right? Multicollinearity is when we have predictors in a model that are highly correlated with each other. So they're kind of providing information about the same thing.
Or maybe what is the other weird thing?
Heteroscedasticity, where we have correlated errors. And we have,
Okay.
So heteroscedasticity is when the error term is non-constant, and for higher values, we might see more spread. Clustering can be a source of that, for sure.
Okay.
So clustering can definitely lead to, so the idea here, right, is if we've got one country that we observe 10 times, and it has a really low life expectancy, right? Let's say this country over here at the bottom, the error term on that is super, super low, right?
Mm-hmm.
And we've got 12 observations of that country. I'm sorry, so this has huge error on it, or this one as well. We have huge error here, and we've got repeated measurement on that. So what we're going to get is just a really big spread on our error term, because we've effectively got this error times 10 in our model at a really high range of the distribution, because we've got 10 observations. So at that stage, we're just going to get a really wide spread here. So clustering can definitely be a source of heteroscedastic error. No
Okay.
about that. Those because it's a source of correlation in the data that our model has not accounted for.
Okay.
Yeah. And it's, in this model in particular, it's going to be more pronounced at high ranges of the data. And we have repeat observations. So yeah, we're going to see non-constant error in this for sure, in a way that clustering would help us tackle.
Okay.
Yeah. So clustering is definitely a source of correlation in the data. And if we don't adjust for it, it's a source of unmeasured correlation in the data. And remember, in a normal likelihood, that's all going to go into the error, right? That those correlations that are unmeasured are all going to go into the error. So we could have observations that are highly correlated with each other in their error terms.
Okay, that's really helpful.
That can really screw up your inference. This is what Nate Silver argued was largely the reason that the polling kind of industry got the election of 2016 so wrong, was that all of the data was clustered but biased in the same direction. And so the error terms were all pushing down in the same direction. And so, his model gave a 20-30% chance of Trump winning the election, and everyone else gave it less than 1% chance. Right? And it was because all those polls were biased in the same direction, and his models attempted to adjust for that bias with this kind of multi-level post-stratification framework that the book discusses very briefly at the end of the chapter. So serial correlation in your errors can be a huge problem that these methods are really good at adjusting for. Okay, other questions? This is good stuff, and y'all are kind of thinking ahead again, right? The variance structure here is what we're after. And the multi-level modeling really, really gives us power to control and estimate the variance structure of our data. Okay, cool. So here, right, this doesn't look, so this is if we completely pool everything, and this is just what the observed data looks like, right? And it's pretty clear there are some patterns going on here, even without pulling this apart. This looks like a mix of distributions. Let's break it out by continent, right? So here we have a kind of tragically low modal life expectancy in Africa across the data, right? And then we have, kind of various skewed distributions of life expectancy across other continents, right? So that's one kind of source of clustering, is continental clustering, that countries within continents tend to be similar. But we can even see, right, in Africa, we have some very high life expectancy countries and many very low life expectancy countries, where in the Americas, the kind of yellowish green, we have some very low life expectancy countries and some very high life expectancy countries. In Oceania, tends to be clustered over to the right. So even within continents, though, it appears that we don't really have clean distributions. It appears that there's kind of sources of variation underneath the continent, too. So let's go to the country, right? This is within country variation. Now, this is really hard to read, but now I've broken out each line as a country across continents. So country level differences could be a source of clustering here. Time could be a source of clustering here, because remember, we're measuring from 1955 up through 2012, and life expectancy is increasing over time. So we can see, right, that the bunching of these points we have a pretty big spread on each of those points, but there is a really clear linear trend over time. And then within continents, we see different magnitudes of slope on those lines. We're not going to address that today, but we'll address this next time.
I'm sorry, question. On the previous slide, each dot is a different country?
Yeah.
Okay.
Each dot is a country, and the x-axis is time. So for 1955...
No, don't do that.
These are...
Sorry.
No, you're good. I understand. Mine is singing in the other room. So these are all dots that represent individual countries in 1955, right? These are dots that represent individual countries in 1960.
Independent of the continent, right?
I'm not doing anything with continent there. This is adding continent, right? And I've jittered it, so I spread those lines out. But the blue here is Europe. The light, green here is the Americas. The darker green is Asia, right? So here I've used color to pull continent out. And what I've done here is I've also fit a regression line to every continent to show that there's differences in the magnitude of this increase in life expectancy across continents over time. But actually, it's a pretty small difference in magnitude, right? Asia looks like it's seen the highest growth. Okay, so these are all different sources of clustering, right? The continent is one clear source of clustering in the data. There are very pronounced differences across continents, but there are very pronounced differences across countries within continents as well, right? There's something going on with time, where there's an increase over time, and it looks like those increases over time may be different across countries and continents. All of those are sources of clustering in the data. And to improve our estimates for life expectancy, we need to account for them. So let's think of intercepts as regression parameters here. And let's move over to the no pooling model. We can think of an intercept, right? We thought of it last time as the global mean for the data, right? The alpha we estimated was a single mean parameter for the full data. What if we constructed a model where we predicted at the life expectancy for a country based on an intercept for that country, right? So we're going to give an intercept for each country in the data. We're going to use the same prior we used before, right? But the only thing we're going to switch out here is instead of a single alpha now, we're going to have like 146 or so, however many countries are in the data. Okay, so pretty simple to estimate. We've estimated models like this before. You just want to make sure to turn country into a factor before you estimate this model, or make sure it's an integer. So it needs to either be a factor or an integer. And so we can estimate this model just as we've done before. So this is a lot to look at. Yeah.
I'm sorry to interrupt. I know we covered this, but I'm trying to make sure I understand. You're doing intercept by country because it's categorical, and we do the multiplication when it's continuous, right?
You mean
when we want to mix a variable?
So for an interaction term, yeah, we do multiplication. For so these are that's a different topic, right? An interaction. So I'm going to show. I'll come back to this in a sec, Warren. I have an example that I think will illustrate the difference well.
Thank you.
Yeah. Yeah, an interaction is a different beast. Effectively, this is an interaction model, right? Where what I have here is an intercept for each continent and a slope. So I have a linear term for year that's interacted with each continent to give each continent its own slope. So that's what an interaction model of continent by time would look like. Effectively, what we're doing here is we're not even modeling time. We're going to have a flat line for each continent. No slope on it at all. We're going to predict the same value for each year of the data for each country, which is not a great model, and we'll do something better in a second. Okay. Any questions about how I estimate this or about the specification?
Would we ever, I'm just trying to wrap my head around it. So the priors of 55 and 15,
yeah,
would assume those could change by either continent or country could. Yeah. Maybe I'm getting ahead of myself.
You are, but it's a good place to go, right? That maybe we want priors that respond to group differences in the data. Mm-hmm. Yeah, So we could like manually specify priors for each country if we really wanted to do that. We're going to go
Okay.
with multi-level model is we're going to have an adaptive prior, right? A prior that is shaped by the distribution of countries in the data. Yeah. Now this is a pretty broad prior, so effectively I'm letting the data and the likelihood dominate the posterior, right? I just want to give a weakly informative prior here to let the model work. Because again, this model says basically, life expectancy could be anywhere between 25 and 85, right? Which is the full range of possible values in the data for the most part. So it's not especially informative. If I wanted to, yeah, sure, say I had prior information that I thought that some continents were lower than others, then I could manually specify priors for each country within continents. It'd be tedious, but I could do it. Okay, but we'll get to the adaptive prior thing in a second. Okay, so cool. Any questions about how I estimate this? How we add the kind of fixed effects. So this is often called the fixed effects model. Sorry, I just got important text. The fixed effects model, right, estimates a dummy variable for each unit in the data, right? And what that's going to do is it's going to constrain it such that we get a single estimate for each data. And effectively what we're looking at for each observation is the difference from the mean value within that unit. I'll show you what this looks like in a second. Notice I'm using that same exponential prior, yada, 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 right? But the bracket notation here allows me to get that estimate per country. And this is what the posterior looks like for the first 26 values of alpha, right? But here I'm going to have a sigma parameter and then a number of alpha parameters that's equal to the number of countries in the data, right? So I'm going to have like 147 parameters. And so that's really difficult to look at. So we're typically not going to look at results in this way for this kind of model, right? But nonetheless, here it is. Now, we get now in the frequentist framework, these alpha parameters will be virtually indistinguishable from the empirical means for each group, right? That if we're not putting a prior on our model, as we do with Bayes, the parameter for the intercept will be the group average, right? And so each observation will be measured relative to that group average. In the Bayesian context, our posterior is not going to be exactly equal to the empirical mean, right? Because we are using Bayesian methods. And remember that our estimate for alpha is going to be proportional to the average value of life expectancy for that country J times the prior for alpha J, right? So we're going to sort of nudge each of those empirical means a little bit towards our prior. In a frequentist model, we're not going to get this. But in a Bayesian model, each of those intercepts is going to get nudged a bit towards the prior. And the extent to which it's going to get nudged is going to vary based on how far away it is from the prior and based on the amount of data we've got for that individual country. I'll show what this looks like in practice in a second. Any questions about this? So this is kind of, remember, this is just the numerator of Bayes' theorem, right? That the posterior is equal to the likelihood times the prior divided by the total probability of the data, which we usually ignore, right? So that our parameter estimate, our posterior parameter estimate, is proportional to the likelihood times the prior.
I have a question.
Yeah.
So is there, I don't know how to phrase this. Is there a, is it like the frequentist and Bayes versions of this are like toolboxes that you can use to specific data when you get at this level of hierarchical modeling where it's like certain data would work well in a frequentist versus Bayes, or is it just like you're doing it differently and the error is going to show up differently?
Yeah. So good question. When we have a lot of data, the frequentist and Bayesian estimates with, weakly informative priors will be often indistinguishable as parameter estimates, right? So
Okay.
if you've got a ton of data, the frequentist and the Bayesian models are going to give you really similar inferences. But you lose the ability to do posterior prediction and simulation, right?
Okay. Yeah.
So, you can use all kinds of tricks like bootstrapping to get similar kinds of, uncertainty intervals and things like that in a frequentist framework, but you get those automatically with Bayes. So I think the downside to Bayes is always just computing time and complexity.
Mm-hmm.
The upside is pretty high. So,
Okay.
You might, and I'll show you all at the end of the semester how to fit every model that we fit using just basic frequentist software in R. The upside there is it's quick, right? And if you're just kind of iterating over models, then yeah, do it with a frequentist model just to get your head around what's going on in the data. And then maybe for your final model, go ahead and run it through MCMC. Now, some of the multi-level models we're fitting are much easier to fit with MCMC than they are with frequentist algorithms. So MCMC is actually a benefit in terms of ease of use for multi-level when we get to really complex structures.
Okay, thank you.
Yeah. Yeah, I mean, the cost to Bayes is always just kind of, you have to think hard about what you're doing, right? And you have to, sacrifice some computing time. That's it, though. If you feel comfortable with that, there's really no cost other than time, which is not trivial. Okay. Other questions? No? Okay. So intercepts are, in this case, right, in the frequentist case, they're strictly the average. In the Bayesian case, they're the weighted average of the empirical mean and the prior. But this is important in the frequentist case and in the Bayesian case, that sticking the country at the empirical mean of the data gives us, is effectively ignoring information from other countries when it fits that. That's why we call this the no pooling model, right? The only source of information about a country's life expectancy are the observed values of life expectancy in that country, right? There's no information about life expectancy in other countries that's allowed to come in to this model for each unit. And we also can't do things like fit additional parameters at the continent level, right? Because continent is constant within a country, right? And so the regression model won't allow us to account for any variation at higher levels. So effectively, why this is called no pooling is there's no pooled information from anything other than the individual units, right? The country is the only unit that we get information on life expectancy for every single country. So we take the maximum of 12 observations for each country, average those for each country, and that becomes our expected value. And in the Bayesian context, it's that times the prior that becomes our expected value. Let's look at what this looks like. So here are the model predictions from our new no pooling estimate. Okay, the dashed line is the is the mean of the data, right? Now the red dots are our model predictions, and the black dots are our observations. And we can see toward the middle, the black and red are basically on top of each other, right? Maybe I'm going to zoom in on this for a second. Right here, right in this mid-range of the data, we don't see much of a difference between our model estimate and our observed data. But when we get over here, more toward the extreme, we see the red dot slightly nudged toward the mean, right? And that's our prior working. It's saying, our prior says this is the distribution, and it makes those values closer to the center of the prior more likely than those values further away. So it's going to nudge those extreme values in just a little bit, right? It's not dramatic, but we can see here down at the low end, right? These get nudged up a bit. And at the high end, these get nudged down a bit, right? And that's the impact of the prior on our inference. This is called regularization, right? Or shrinkage. What we're doing is we're shrinking our estimates down toward the prior. But the impact is pretty small in this context, right? The data is largely overwhelming the prior because 12 observations is enough to come up with a pretty strong mean. And in a lot of these countries' cases, we have pretty narrow bands around those means. Let's look at this, right? So for country 1, we have a mean of 37 with an 89% interval of 35 to 40, right? In country 5, right, our interval is 65 to 71, right? So those are pretty narrow around each country. They're not exceptionally broad such that the prior is going to be able to dominate that. And remember, we have a pretty diffuse prior. So, yeah. So shrinkage, right, or regularization, right, is a way for us to basically not, it kind of is a slight nudge against overfitting the data, right? Remember, we talked about overfitting the data is kind of perfectly passing through every single point in our regression model. And the fixed effects or the no pooling model really, really wants to do that. It wants to predict exactly what we see for each country, which is the definition of overfitting, right? The Bayesian model is going to pull us in just a little to make us, kind of avoid extreme overfitting, but this is still relatively overfit. So regularization, right? Our model shrinks intercept estimates by gently nudging them toward the prior. And the shift is larger when the prior is narrow, when we have a strong prior. Now remember here we have that 55-15, and right, the interval extends plausible values between plus or minus 2 standard deviations, so 35 and 85. So all of our observeds fall within that range. Prior is pretty broad, so our prior is not going to have a huge impact on shrinking estimates. Our prior is kind of broad, so it's going to have a small shift. But the shift is larger when the group mean is far away from the global mean, right? Which we see here and here, right? The further it is away from that prior, the more it's going to move. It's also we're going to see larger shrinkage when we don't have as much information about a particular unit, right? And this applies to this no pooling model as well. If we only have 3 observations on a unit, right, the prior is going to have more influence than it will if we have 12 observations per unit. So we'll see more motion in the posterior relative to the observed when we don't have a lot of information on a unit. Right, the shift is smaller when the prior is wide, when the group mean is close to the global mean. Again, here we see virtually no difference between the empirical estimates and the posterior estimates. And remember, 55 should be where we see virtually no movement at all. That is the center of the prior distribution. When the group mean is close to the global mean or close to the center of the prior, and we have many observations per unit, right? So this regularization or the shrinkage is an important thing we get with the Bayesian model that we don't get with the frequentist model. It helps us avoid overfitting the data. Now we're going to extend this into the multi-level model, right? This regularization is a key reason to use the multi-level framework because we can split the difference between this model where we predict the same thing for everything, but we don't use any information on individual country differences. We don't use information on the clusters. We just estimate the same value for everyone. We can split the difference between this model and this model where we predict each country is exactly at its mean and we overfit the data, right? So right now I've shown you the no pooling model underfits the data. The no pooling model overfits the data and the complete pooling model underfits the data. In this approach, we learn too much from the data. We overtrust the data, right? Because effectively what we're doing is we're saying all countries are fundamentally different from each other, and there's nothing about country B that tells me anything about country C, right? And that can't be right. Country B can certainly give us information on country C because they're all examples of groups of human populations, right? And human populations all have similar characteristics when it comes to life expectancy. Now, there might be clustered differences across them, but to completely discard information about the population of countries when we're estimating life expectancy for a single country seems kind of foolish. So what we're going to do is we're going to develop an approach that can use information on all countries to help us improve our estimates for single countries. So, right, the no pooling approach, right, just to kind of, I want to get these no pooling and complete pooling models in your head, right, because these are the kind of alternatives that we're typically choosing from in multi-level. In the no pooling approach, we estimate country intercepts with 2 pieces of information. We only use 2 pieces of information to estimate these. The observed years of data on the country level life expectancy. So even though we have like 600 or some, I don't know, 1,000 rows of data in this table, for each country, we're only using 12, right? At most 12. The rest are discarded. So we get those 12 years of data on county level life expectancy that are assumed to follow the normal likelihood. We get the prior, and that's the only information that each intercept is using. It's only using those 2 pieces of information. And they ignore information on life expectancy from other countries. Right? So it's a within unit model. Sometimes you'll hear these as between and within. The no pooling model is a between country model. The no pooling model is a within country model. So again, this is often, if you ever hear the term fixed effects, it's referring to a no pooling model, right? This is something you see a lot in econometrics and in causal inference, right? Is a model where we actually, based on trying to identify a causal effect, we might say, well, I want to look at the effect of some treatment on the trajectory of an individual over time. So I really do want to narrowly constrain my model to a within unit change over time. Now, I would argue that that's also going to overfit, right? Because it assumes perfect measurements and it assumes no error in, that there's nothing exogenous happening in the system that could kind of move things around for that individual over time. It's a really strong set of assumptions. That fixed effects model, though, is a no pooling model, right? Where it discards information on other units to look exclusively within a single unit. That Bayesian approach is going to give us a similar framework, but that prior regularization is going to slightly nudge things. And again, this overfits the data. So what this is going to do especially badly is prediction, right? With that overfitting, we're going to end up with more extreme predictions than we should actually see, and our prediction error will be relatively high, right? Because we've overfit the data. So that means, if we have, only 12 points of observation for a particular unit, we don't actually have a lot to predict on with only those 12, versus if we had 1,000. So why don't we take 5 here, and we'll come back and we'll start to talk about the multi-level approach now that we've kind of motivated it with, what's wrong with the complete pooling and no pooling approach. When we come back, I have 10:54 on my clock. Let's say 10:57. We'll reconvene.
We'll be in.
All right, we are back. Okay, so. The fixed effects model is one I typically avoid using for all of the reasons I've described above, right? We typically overfit the data, and there's an approach that can do better. So let's kind of start talking about the partial pooling alternative. And partial pooling is another way to say multi-level, right? So we have one model where we have ignored cluster differences. We have another model where we have paid too much attention to cluster differences and ignored global information, right? So there's an approach that we can use. So in complete pooling, right, we assume all units are the same. In the no pooling approach, we assume all units are fundamentally different, and unit A can't teach us anything about unit B, right? Unit A is fundamentally different from unit B. The partial pooling approach assumes that all units are in fact different, but come from the same larger population and share some characteristics. So we're going to use information on the clusters to estimate those intercepts, but we're also going to use information from the global population to tell us where those intercepts should go and how different they should be from each other, right? We're going to set a mean and a variance parameter on those global intercepts, right? So we're going to add what's called hyperparameters to our model. We'll get there in a little bit. So the basic approach is that we're going to add a little complexity to our model, and we're going to split the difference between the complete pooling and the no pooling approach, right? We're going to get the benefits of each, where we're going to get information about the full population, but we're also going to get information on the clusters, right? And we're going to leverage both to improve our inferences. So we're going to estimate an intercept for each country, but we're going to borrow information across countries to help us estimate those intercepts. Because each country is a subset of the broader population of countries, right? We're recognizing that there are similarities across these units, and we should use information on the whole population to help us understand the distribution within a country. So we're going to add what's called an adaptive prior. And the prior itself is going to get estimated from the data. And that's going to become part of our intercepts, right? In the book, he works through examples where we estimate adaptive priors using parameters for the mean of the intercepts and the standard deviation of the intercepts. Here we're going to focus on estimating models with only a standard deviation term for the intercepts to make it a little simpler to understand for now. So we're going to work through the reed frog example from the book. So this experiment, so this is a paper actually written by Ben Bulker, who was one of the developers of the LME4 package for R, so this is the kind of most used package for estimating multi-level models in R. Comes from a good source. So here, what we're looking at is an experiment where the likelihood of survival of a group of tadpoles is a function of its population density within a particular pond, right? And whether they were exposed to predators. So here we're asking, right, how many tadpoles of the initial group survived? And was there something about here we have tanks, right, of tadpoles? We could think of these as ponds. Is there something about the individual pond or tank itself that structures the likelihood of surviving, right? So density is the number of animals, of tadpoles that started in the tank. 9 is the number that survived, and prop serve is the proportion of survivors, right? And I guess this is whether it's a big or a small tank and whether they were exposed to predators or not. So poor tadpoles in the name of science. Okay. So the complete pooling approach, right? What we're going to do is we're going to estimate survival probability by estimating a single intercept for all tanks, right? And we're going to put a prior on that that's pretty broad. We're going to say this is a binomial model with a logit link, right? We're just going to let it go. We're going to say the log odds of survival are somewhere between -3 and 3, right? Which is basically, the probability of survival in the average tank could be anywhere between 0 and 1 is what we're saying with our prior. It's really broad. So I'm going to set my data up. We're going to make a tank index, right? We don't have a tank index here. And what I want is basically a 1, 2, 3, 4, 5, 6, because each row is a tank. And so to estimate my no pooling model and my partial pooling model, I'm going to need an index to identify each tank. So I'm going to go ahead and make that by saying 1 to n row reed frogs, and that's going to give me that integer for each row. And that, assigning it as a mutate, is going to assign it 1, 2, 3, 4, 5, right? And I'm going to select tank, serve, and density. Those are the only 3 variables I'm going to be working with. I'm going to estimate my binomial model where density is n, right? Density is the number of tadpoles that could have survived, and serve is the number that did survive, right? So 1 minus serve is the number who died. Survival is our 1 in this case, and death is our 0 in this case. So our binomial in P is binomial density P, where logit P is equal to alpha, and alpha has that normal 0, 1.5 distribution as a prior. Any questions about this model? Okay. Here's our model posterior. Someone want to tell me what's going on here? This is our posterior for P across tanks, right? So the x-axis is tanks, the y-axis is the likelihood of survival across tanks. What's going on?
There's a handful that are surviving, and then there's a handful at the bottom that are...
Don't focus on the scatter plot. Focus on our posterior, right? Our posterior is the ribbon. What is going on with our posterior for P, the probability of survival?
Seems rather narrow.
It is. Would we describe this as a complete pooling model or a no pooling model?
Looks like no pooling.
There's only one other option. It's the complete pooling model, right? Why would I, so what is our posterior for alpha saying here? Right, this gray band is our posterior for the probability of survival. What's it effectively doing? The expected value of survival, we could read this off as the expected value of survival is about 0.73 in tank 1, and in tank 2, and in tank 3, and in tank 4, and in tank 5, right? So what's our posterior telling us?
Just the median.
Yeah, it's telling us, the mean, right? But it's telling
Yeah.
that the likelihood of survival is the same across tanks based on this model. Our expected survival probability is the same for every tank. And that's going to be really close to the empirical mean, right? And it's going to be effectively the empirical mean, be proportional to the empirical mean times the prior, right? And we see that really narrow band on it. We're really sure where the mean is, right? The model's pretty darn sure where the mean is. Has no problem estimating that. If we were to do this in terms of a prediction interval, it would be very wide. This is just the posterior interval for alpha on the probability scale. But this is the complete pooling model, right? We haven't used any tank-specific information here. All we've done is we've used all of the observations and treated them the same, and then we're going to make the same prediction for every tank. That's what our model says to do, right? It says that survival is distributed binomial in P, and it says that P takes on a single value, and that's alpha. I'm sorry, it should be logit P. Miswrote it in the specification. At least I estimated the model correctly. So it generates a very precise prediction, right? Narrow interval. And it makes the same prediction for every tank in the pond, right? This is in terms of the expected value. But it underfits the data, right? We haven't used all the information we've got. So we are going to have relatively high errors in terms of the difference between the observed value and the expected value. So we can make much better predictions by estimating a more complex model. Let's try that. Let's estimate a no pooling model. What's the difference here? Someone tell me the difference in this model specification. Again, that should be logit P. I'm sorry that I didn't write out the specification correctly. Ding me 2
We're like
points.
sunsetting by tank.
Right. So how many intercepts am I going to have here?
You should have 10.
So I'm going to have as many rows as there are in the data, right? So I have 50 tanks, right? Tank goes 0 or 1 through 50, or 49 or 48 or so, right? I'm going to have that many intercepts. So we're going to estimate this model. We're going to use the same very broad prior. And this is what I get now. Here, I've used color to indicate the population size of the tank. So density is a measure of how many tadpoles started in the tank, right? So we could think of that as having more information about survival because our initial N is higher. So we had more trials to estimate P. So the filled dots are the empirical proportions, and the hollow dots are our expected value of P, right? Where the y-axis, again, is survival probability, and the x-axis is tank number. What do we see here? Someone describe, so here, we're clearly not predicting the same thing for everybody, right? We have 48 posteriors, right? Because we have 48 alphas. Before we had one posterior that we just moved across each tank. Now we've got 48 parameters. So are there any patterns that anyone sees here? What should we expect in terms of shrinkage when we have low information in a tank? In terms of how much influence should the prior have when we have low information in a tank? All right, let's go back to...
So little information means we have a stronger effect from the prior?
Right, so if we don't have a lot of information in our likelihood, then the prior has a bigger influence, right? Now, here, These are our low population tanks where we only have 10 trials, right? 10 tadpoles. Over here, we've got 35. So notice the gap between the observed and the estimated is relatively large in these low population tanks, right? Here we observe 100% of the survivors, but our posterior says that's probably not right. If I observed more data, I think it would probably go down a bit, right? And so the posterior interval, right, doesn't even include 1, and it's pushed down, right? Pushed down toward the prior. But when we get over to the blue points where we have a lot of information, right? This is 35 trials per tank, right? We've got 35 tadpoles in that tank, so we've got 35 chances to observe survival, versus here we've only got 10 chances to observe survival. Notice that the MAP, maximum a posteriori, the kind of center of the posterior, is pretty darn close to the empirical mean, right? We've still got wide intervals, and we often see wide intervals when we're working in this no pooling approach because we've only got, so much data. We have a limited amount of data to estimate our intercept. So we do get pretty broad uncertainty, but the gap between the observed and the posterior is pretty small when we have a lot of information. So there's less shrinkage when we have more information, or when the observation is close to the center of the prior. Right? In this case, the center of the prior is 0.5 because we centered it at 0. And on the log odds scale, right, that's going to give us a probability of 0.5. So this is the no pooling model. So we're cool on what the prior is doing here, that it's regularizing the estimate, it's shrinking the estimate toward the prior, and it does that less when we have more information. Yeah? So do you think we're going to see more or less? Well, we'll get there in a second. Okay, so that's the no pooling model, right? The complete pooling model, same prediction for everybody. No pooling model, different predictions for everybody. But again, the only thing we're using to estimate the intercepts here are the individual tank rows, right? So in this case, it's getting estimated from one row of data. Each intercept is getting estimated from the one row. But it's kind of unpacking it and thinking, okay, this is 35 observations, this is 10 observations. Right, remember, we can kind of think of the binomial count model as in Bernoulli trials. Okay, questions? So here is our multi-level model. Okay, we're going to use an adaptive prior for tank intercepts for each tank J, right? Now our prior has its own prior, right? We're nesting these models together, right? So effectively, we're building a model on top of our model. We're saying, yeah, I want intercepts for each tank, but I want those intercepts to follow a probability distribution. I don't want them to just be the average. I want them to be sampled from a probability distribution that has as its middle the average for all tanks, right? So effectively, what I'm saying is I want those intercepts to come from a normal, right? I want extreme intercepts to be unlikely. I want most intercepts to be close to the center of the average of all tanks. And then I want, the actual value of it, the likelihood of a particular value to be proportional to the probability density of that normal curve. This all sounds kind of crazy, and it is a little crazy. Effectively, what we're doing is we're adding priors and parameters to our priors themselves. And this is why the multi-level approach makes a lot more sense in the Bayesian framework than in the frequentist framework. Because adding additional parameters into our priors in a Bayesian context seems less weird than giving a parameter a probability distribution in a frequentist context, which is actually what's happening in the multi-level frequentist context. It's this kind of pseudo-Bayesian thing that you can do, or we could just do it as we've been doing, right? Now this sounds strange, but it actually doesn't look that strange given what we've seen all semester. Okay, so these are called hyperparameters, right? When we put parameters inside of our prior, we call them hyperparameters, and that's common language you'll see in multi-level modeling, right? Those parameters associated with our varying intercepts, right? Here we're you might call it, hear this called a multi-level model or a varying intercept model, because we're allowing intercepts to be a function of tank cluster, of tank number of some cluster. So let's kind of talk through this, right? These two pieces look exactly the same as before, right? And again, this should be logit. I'm sorry, I misread all these models. Survival is binomial. The logit of P is equal to alpha J. Alpha J is distributed normal. But instead of saying that it's normal 0, 1.5, right, we're going to say it's normal with alpha bar and sigma. So we don't know exactly where this distribution is centered, right? We want it to be centered at the mean value for tanks. And we're going to have as a prior for that it could be, that mean could be anywhere. I have a very vague prior on that. That alpha bar 0, 1.5. I do need to have priors for my hyperparameters, right? But I'm letting it be wherever the data wants it to be with the 0, 1.5 prior, right? And I'm going to put sigma now, right? We didn't have any variance parameter on this at all. We had the 1.5 before, but now we want to estimate the variance across tanks as a regression parameter, right? So we're going to get an estimate of how different the tanks are from each other. So the distribution of tank intercepts now has parameters that are going to be estimated from the data. What we're going to do is we're going to take the population of tanks to draw out a normal curve from which we're going to sample our individual intercepts, right? That becomes the likelihood for the average value for each tank. Rather than just letting it be estimated purely from the empirical data, now that global mean value across tanks is going to act as an additional prior that nudges things closer to the group mean, right? So now we have two sources of shrinkage. We have whatever our priors are in the model, and we have the multi-level distribution for the tank intercepts. So we have kind of two ways that now, where we had one source of regularization before in our prior, now we have another source of regularization, right? And it's this multi-level specification. So our intercepts themselves have a distribution, right? And this is they have a likelihood. This is different than what we've done before. So we have the binomial likelihood, but we also have a distribution for our parameters, for our tank level intercepts. That's going to make those extreme values on a normal more unlikely, right? And it's going to pull those in a little bit. It's going to make values that are closer to the middle. It's not going to do very much to those. Or those for which we have a lot of data, it's not going to do very much to those. Let's take a look at this. Here's how we estimate it. And it doesn't look that different from what we've been doing, right? This is identical to the last specification, survival, binomial, density P, logit P is alpha tank. Alpha tank, the difference here, right? We're going to sub in A bar and sigma. And we're going to put our prior for the distribution of intercepts. Where is the distribution of intercepts centered? Well, I don't really know. Put it wherever the data says it should go, right? That's a vague prior. Same thing for sigma. How different are the intercepts from each other? How different are tanks from each other? I don't really know. An exponential 1 allows for a lot of space on the logit scale. Those are vague priors. Now here is what we get when we just look at our two hyperparameters, A bar and sigma. Okay, so A bar is, again, the average intercept for a tank, right? This tells us where the center of the tank intercept distribution is, and that's at 1.34. That could be informative. It says the average tank has a 1.349 log odds of survival, right? So we could exponentiate that to get it into an odds ratio. We could inverse logit it to get it onto the probability scale, right? So just, so we feel good about interpreting logits. Let's in logit 1.349. So the average tank has about a 79% probability likelihood, right? Now sigma is our estimate of how different tanks are from each other, right? And what do we see here? A sigma of 1.6 with a posterior interval between 1.3 and 2 says tanks are pretty different from each other, right? So a normal centered at 1.34 with a standard deviation of 1.6 is a pretty wide normal, right? That's saying tanks are really, really different from each other. So this sampling distribution is going to allow those intercepts to be far apart. And remember, we estimated those from the data. We put a prior on it, but we estimated it from the data. And this is fundamentally different than what we did in the no intercept model. So again, when we're looking at these, alpha bar is the posterior for the center of the distribution of tank intercepts, and sigma is the posterior for the standard deviation of tank intercepts. Those come from a probability distribution now. And this is why multi-level models are fundamentally different from no pooling models. Now, here's the tank intercepts. We're not going to actually pay attention to this, but we do want to look at like our, effective sample size and our R-hats, and these look fine, right? As they did over here, right? Our effective sample size and our R-hat's close to 1. Effective sample size with 4 chains, we have 2,000 actual samples, and over 1,000 is fine. Above 1,000, we estimated this really well, right? We have a ton of information here. A little less information on sigma, but enough to use the chain effectively. And then for each intercept, sometimes we're going to see ineffectives or R-hats that are, don't look like we have a ton of information here. And that might be that we don't have much information on that cluster, right? So the effective sample size for small tanks might be systematically lower than the effective sample size for large tanks, right? Because we have more observations that we're basing our estimate for the, difference of that tank from the population of tanks on. So here's what our model inferences look like. This is the complete pooling model, right? We predict the same for everybody. And again, color corresponds to the size of the tank, just so we can see the impact of, the amount of information we've got on the shrinkage. So here, right, we're predicting the same for everybody regardless of anything. We could do better. No pooling. Here, we have a different prediction for every tank. And we can see the light dot is the observed, the dark dot is the center of the posterior, right? So again, we see that kind of shrinkage is lower in the high information tanks than in the low information tanks, right? And here's the partial pooling model. And we can see these give similar inferences, right? In the partial pooling, we move these around a little bit less in some cases, a little bit more in some cases. In the high information cases, these are moving less, right? It depends on where they are in the distribution relative to the global population, right? But the no pooling model and the partial pooling model are not worlds apart, right? And they typically won't be worlds apart. But they're using information on the full population, and that makes inferences work a little different, and it means we get some extra information that can be really cool to work with. So here I want to show this to you on the scale of error, because where the partial pooling model really outshines the no pooling model is in its prediction error, and in this case, just the observation error, right? So on the complete, here what I've done is I've subtracted out the observed value from the center of the posterior inference for each tank, right? So this is just the absolute difference from the observed, right? So I took the absolute value of the difference between the observed and the expected value. So for the complete pooling model, obviously we've got a ton of error, right? When we look at the gap between these points and these points, except for those that are close to the mean, our error is really high, right? The no pooling model has much less error, right, than the complete pooling model. But the partial pooling model has less error still. At the same time as it has less error on the observed, it will also have less predictive error, right? Because it shrinks those estimates in a way that's adaptive, right? So it could be the case that our prior here was shrinking things toward our prior, but our prior wasn't really informed by the data. When we use this adaptive prior to shrink things toward the global mean, we improved our inferences, right? So this partial pooling approach, except for those cases where we had a lot of information, right, in those high density tanks, then our errors are really not distinguishable. But for these low information tanks, we can see that we did way better, right? The pink dots are much better in the partial pooling approach than the no pooling approach, right? 0 means we have no error, right? And so the smaller the value is here, the closer we were to the actual value when we computed our expected value. So this partial pooling approach splits the difference, but you really gain a lot when you do it, right? The cost is you add complexity, right? We're adding hyperparameters to our model, which sounds crazy, and it is a little crazy. We're adding a model to our model, right? We're adding effectively a second regression inside of our regression. That's why it's called multi-level, right? We have a second model inside of our model. But when we do that, we get a lot back. So it becomes more complex to think about what we're doing, and it can become more complex to estimate the model. But there's a really strong payoff, right? We split the difference between complete pooling and no pooling. We are using information from the full population. Generally, we're going to not only fit the data better while avoiding some of the costs of overfitting on prediction, we're also going to predict out better later, right? So this kind of threads the tension between overfitting and underfitting by maximizing the information. So we're getting information within clusters and between clusters, right? That global we can think of as the between cluster parameters, right? This alpha bar and this sigma are kind of telling us what's going on with the population of tanks at the same time as we're estimating intercepts for each tank. So we're getting information on the unit, but we're also getting information on the population, right? So now we know that the tanks are pretty different from each other. And we didn't necessarily know that just from the no pooling model. We didn't get a parameter that told us how different the tanks are from each other. And now we have that. And it turns out that's going to be really useful. All right. This is a lot. So please ask any questions you have. We're going to do more. This isn't the end. But please slow me down and ask questions. This is, this is a new topic. And I do want to make the case to you that the multi-level model should be your default approach. When you have any kind of clustering in your data, you should default to a multi-level model, unless you have a strong reason not to. You get most of the benefits of the no pooling model while also leveraging information on the full population. So we want to get comfortable with making these, right? Because as you move forward in your career, these should be a tool that you use routinely because they're incredibly powerful. If you have any kind of clustering in your data, this should be a tool in your belt. And in my research, this is the default model I run, right? I don't think I've published much of anything in the last few years that hasn't had a multi-level model at the center of it. Okay. So no questions?
No, Frank, but I really liked that preach.
The which?
I felt like you just preached multi-level to us.
Yeah, the gospel, the good word about multi-level models. Yeah, no, they are great. And once you're in a Bayesian framework, right, there's not much cost to estimating them because you're already doing a multi-level like thing, right? This is kind of very consistent with the Bayesian philosophy of how to do data analysis, is to let the data really inform what we're doing, right? And but at the same time to not overtrust things, right? To kind of pull things in a bit.
Can you also run Poisson models in the Bayesian?
Yep.
Framework? Shush.
Yep.
Okay.
We can run any of the models that we have estimated so far with a multi-level, right? The only thing we have to do is just change the specification of our model a little bit, right, to add in these hyperparameters. But this could easily be a Poisson, right? And I will probably show you an example of that next week. There's an example in the book of doing it. But remember how we talked about over dispersion in Poisson models and how we would use the negative binomial?
Yeah. Okay.
So in that context, right, we have sort of extra inflation in our counts or extra inflations in our variance, right, that we've been calling over dispersion. And it turns out that varying intercepts are a great way to model over dispersion. So in a Poisson model, what I'll often do is put an intercept for each row of the data, right? So if I've got 1,000 rows of the data, I'm going to put 1,000 random intercepts in my model to allow each observation to be a little different from where the Poisson model thinks it should be, right? And so that's, we're going to kind of, we learned the negative binomial model and the beta binomial model, but we can actually leave those behind now that we have the multi-level approach because we can model over dispersion with intercepts, which also means we can add other multi-level structures to it. So typically you might have heard, you have to, in a fixed effects approach, right, if we have a group specific parameter, we can't have higher order predictors in there because they're constant within the individual, right? Like if I have a kid assigned to a classroom and that classroom never changes, if I have an intercept for that classroom that's not multi-level, I can't have like anything about the teacher in the model as well, because that's already bundled up in that fixed effect. But in a multi-level approach, I can have those higher order predictors in the model, right? And so we can make inferences about what's going on at multiple levels simultaneously. And that is another kind of real benefit that is a little above what we're going to do today, but we'll get there. Any other questions before we push on? So here we've shown multi-level with a binomial. Next, I'm going to show you multi-level with a normal. So this is the binomial likelihood. You could do exactly what we did here with a Poisson. You could do it with a multinomial. You could do it with any of the likelihoods we've used. Right, but next we'll do it with the normal. So there's our error terms again. Oh, right, and model comparison, right? If we want to really convince ourselves that the partial pooling model is better, right, we can use the widely applicable information criteria to see here that we get a really strong preference for that multi-level model for expected predictive accuracy over the others, right? The WAIC strongly prefers the partial pooling model over the others. It's giving us much stronger expected predictive power than the no pooling model. There's a really cool example in the book that I encourage you to work through on your own, where you actually simulate out new data and then try and recover values with a no pooling and a partial pooling model. And in that context, the partial pooling model outperforms the no pooling model when we actually know what the parameter values are, we simulate them, right? Typically, we don't know what our parameter values are, but in the context of a simulation study where I say, alpha bar is 1.5, tell me what, this particular tank's, mean is, the multi-level model is going to perform better than the no pooling model in terms of prediction. Now, it's difficult to know that in real world context, but our information criteria seem to think this multi-level model is going to do better than the no pooling model. And obviously, it's going to blow the complete pooling model out of the water, right? It's a dramatic increase. The no pooling is an increase over the complete pooling, but the partial pooling is clearly the best performing model by expected predicted performance. Okay. So, yep.
I'm sorry, can you go to the previous slide again? What is the weight there? Is it?
Yeah, so the weight is just a kind of gut check, where is the kind of posterior weight in terms of which model we should prefer. I don't actually understand what goes into the calculation of that because the function isn't well documented. I've tried to figure out what the weight is. It typically goes to the 0 for the difference WAIC, and it's proportional to the standard error, the ratio of the standard error to the difference, right? But I don't understand exactly what that number is because the function doesn't tell me how it calculates weight.
Okay.
But,
I just think.
Sorry, go ahead.
Well, so the number is for the partial pooling is 1, and then it's like a proportion for the other thing. So I was wondering if it was
yes, the number
recognizing something there.
Yeah, the number here is effectively 1. The number here is like 0.006, and the number here is just 0, right? So it's effectively telling us, how much we should trust one model over the other. That's kind of how I've been interpreting these. But you can interpret that as kind of more concretely as the difference in the posterior WAIC, right? So it takes the lowest value and then differences the others. And so this has a 14-point difference in WAIC, but we also want to know, is that a meaningful difference? And so with a standard error of 4, right, if we think of this as approximately normal, that difference is definitely non-zero, right? Because plus or minus 8 here gets us to 22 and 6, plus or minus 2 times 4, right? If we think of this as approximately normal and we're thinking of this kind of implicitly as a significance test, then that tells us that the difference in these two is probably greater than 0. And so we should prefer this model, just by the information criteria, right? Obviously, more should go into how you choose models than information criteria. This is a good gut check on like, is it outperforming it in terms of predictive accuracy?
Okay.
Yeah. So short answer, I don't know what weight is, but I know it's proportional to the ratio of DWAIC divided by DSE. Right. So, sorry, I don't have more on that. Okay. So what does the partial pooling model do to the posterior? These ordinary Bayesian models shrink the estimates toward the prior. The multi-level models shrink posterior estimates toward the group or the cluster mean, right? So the multi-level model is going to pull our prediction for each unit toward the cluster mean, and it's going to pull the intercept estimate toward the global mean, right? So we get, in addition to the intercept itself being pulled toward the prior, right? So we have two sources of shrinkage now. We have the shrinkage we get from our prior, right? So all of the intercepts are expected to have an average value that we fix a prior for. So there's going to be a nudge toward this prior for our hyperparameter. But there's also going to be a nudge given by the probability distribution that we estimate from the data, right? So they're going to be pulled toward the global mean in addition to being nudged toward the prior for our hyperparameter. So we have two sources of shrinkage now. We have the ordinary shrinkage we've gotten from Bayesian models in the past, but now we have this additional shrinkage driven by the multi-level specification, right? So each of those intercepts for the each tank is going to get pulled toward the global average for all tanks. And the extent to which it's going to get pulled is driven by how far away it is and by how much information we have on that tank, right? So this one is one of the furthest away these are all ones, right? But the least amount of pull we get on any full surviving tank is blue, where we have more information on the tank, right? So that point there gets pulled less toward the group mean than this point, right? Because this has slightly less information and far less than these points, which have much less information. And we can see, even though these were all one observed, we have some sampling error. We have some simulation error here, right? Because these are driven by a probability distribution now. Okay. Cool. Questions about the kind of shrinkage features, the regularization features of these multi-level models? This is what helps them avoid overfitting, right? This kind of shrinkage. And I typically think of this, some people will say, well, if the data is measured perfectly, why do we bother with something like this? And in the case that we do have a lot of information, the data is measured perfectly, these models are going to give us inferences that are effectively the same as a no pooling frequentist model, right? But in the context where we might think, I have 10 observations and I have some uncertainty about where the next one's going to be, right? Then this is going to do a better job than saying this is the full population of the data and this is where the mean. Right? It kind of recognizes the uncertainty in the data generating process. In addition to doing a good job of accounting for things like measurement error, we'll get to that when we talk about multi-level models and the imputation of error and missing data. Okay, so what if we have clustering at more than one level? Right, so we clustered at one level there. That was the tank, but there's no reason we can't cluster at more than one level. We often have nested data structures, right? We talked about a student being nested within a classroom, but a classroom is obviously nested within a school, and a school is nested within a district, and a district is nested within a county, and a county is nested within a state, right? And a multi-level model can help us think about the sources of variation at each of those levels, right? So we're not restricted to only thinking about one level of variation. Now we can think about variation at any number of hierarchical levels. So how many levels of clustering are there here in the Gapminder data?
Possibly 3, but like maybe year.
So year, right, could be one source of clustering that we could think observations from 1952 are going to be similar to other observations from 1952, right? What else?
Country and continent.
Right, so we could think that continents, right, countries in Asia are going to be similar to each other. They should have life expectancy values that are similar to each other. And poor Afghanistan, a life expectancy of 28 years in 1952, right? And when you look at these data, you can see the impacts of the wars in the 80s and the 2001 life expectancy. That's pretty something. And then we could also expect that, countries are correlated with each other, right? That the observations of Afghanistan in 1952 should be correlated with the observations of Afghanistan in 1957, right? So we could have correlation across continents, across years, and within countries.
Frank, is there a conflict between doing this because within countries across years, within years across countries?
So we can specify really complex structures later. We're not going to get there just yet. But today, all we're doing is varying our slopes, right? Today, all we're doing is putting probability, on our intercepts. We're putting probability distributions on our intercepts. We can estimate separate slopes for each unit. So we could, for example, allow each country to have its own time trend, right? We could allow each continent to have its own time trend. We could add all kinds of complex structures into this. If you have a good motivation for it, you can do it with this approach. We're not going to do it today, but yes, it's possible. You can add incredibly complicated structures into your data this way if you have the scientific justification to do it.
Could we also do like loose clustering as well? Like, even though, let's say we found another country in 1952 that was very similar in population size to Afghanistan at 84,000, except they were, or what is it? Yeah, 800 and is that 8 million? Anyway, 8,425,600. Like, I guess. Okay.
So what you're suggesting is, I don't know what you mean by loose clustering, but we could think about countries being similar because of their size.
Yes, essentially, but it's not like the exact population.
Yeah, we could have like low economic activity countries, medium economic activity countries, high economic activity countries. We could do similar things with population. Sure, we'd need to split them into categories, right? We typically, when we're estimating intercepts, we want to use categorical variables for our intercepts, right? So if we had some theoretical reason to say that, like, countries of similar population should be similar to each other, then we could do that. I think the motivation for clustering there might be weaker than the motivation for clustering within a country, right? And that I definitely expect. So if you really, let's start with what we think will give us the biggest bang, right? And that's clustering by country. But we could consider doing that if we thought there was some additional variance that we could explain by similar population sizes. No reason not to. Okay, so there is a clear change over time, right? Remember when we looked at the initial plot, we saw a slope of life expectancy increasing across all countries over time. So I want to account for that with a linear term, right? Flash back. Get whiplash here, right here. We see life expectancy going up across countries and within continents. Every continent sees an increase in life expectancy over this time period, right? So let's account for that, but we can do a pretty good job with that with a simple linear term. So that's how we're going to estimate it here. So we're just going to have a beta times year. I'm going to center year at 0 because beta times 1955 ends up with a beta that's really, really, really close to 0. Just to capture that line. Instead, I'm going to make 1952 equal to 0, and then 1957 will be equal to 1, and 1962 will be equal to 2, just to make that beta not quite as close to 0 as it would be if I didn't, subtract 1952 off. And then we're going to estimate an intercept for each country, right? I'm going to center life expectancy to make priors easier. But also remember that when I estimated the fish tank or the tadpole tank model, I had two hyperparameters, right? I had alpha bar and sigma. Now I needed alpha bar because I wanted to, constrain the center of my prior for that normal that was going to draw the intercepts to be driven by the empirical data. But what if I set the center of the empirical data equal to 0, right? With mean centering, with a scale, right? So if I set the empirical center of the data equal to 0, then I ensure that the distribution of country intercepts is going to be close to 0, right? I don't need a parameter for it at that point. And reducing the number of parameters you have to estimate can always make your life a little easier. So in this case, I'm only going to have one hyperparameter. I'm going to have sigma alpha, right? So I have sigma for the full data. So that's, we can think of that as the difference across all units of life expectancy, net of the difference across countries, right? So this sigma, in effect, becomes the within country difference in life expectancy, where sigma alpha becomes the between country difference in life expectancy, because those intercepts are going to account for the average difference across countries after we've accounted for this linear increase in life expectancy across countries over time, right? I'm going to use a broad prior for beta, and I'm going to use these exponentials for sigma alpha and sigma, because I remember before I used an exponential 0.5, but now I've rescaled life expectancy to be on a standard deviation mean-centered scale. So now it only ranges from like -3 to 3, right? And so we don't need quite as big of a sigma prior. We don't need as much weight in the tails. Okay, so I just said a lot.
And Frank,
Yeah.
The reason that you're able to, and that you're allowing yourself, in a sense, to change the values of the countries, that it's really that it's changing from year to year, but the actual value of the year, not country, year, doesn't have any kind of intrinsic information in it.
That's right. Yeah.
Okay.
So the year itself, like 1956, doesn't have information. It's on its own. The only way it contains information is relative to 1952, right? So as long as it's a linear increase, I can scale it however I want. It's going to give the same information to the model. So what we're saying is we expect life expectancy to go up over time, right? And we expect each country's life expectancy to basically be near its average, but pulled a little bit toward the global average. And then it's going to go lower for earlier years in the data and higher for later years in the data. That's what this model is saying if beta is positive, which I know it will be, right? Other questions about what this hyperparameter is doing, right? We have two variance parameters now. We have sigma and sigma alpha. That's kind of new and strange.
I have like more of a like technical, not like about that question. So when you said I just got confused when you said that the year is going to be like 1, 2, rather than like, are you doing that, changing your variables, or is you setting up that prior doing it?
No, I'm changing my variables. So
okay, so
here I'll show you the.
So if we do that, we'll have to recode our variables.
Yeah, you need to recode, right? So here's where I do it in code, right? Is I take the Gapminder data, and there we are. Okay. So I take the Gapminder data. I'm going to center life expectancy by differencing each value from its mean and then dividing by the standard deviation. Right, that's going to give me the same thing as the scale function. I'm going to turn country into a factor. And to center year, right, so I could just divide, like subtract 1952, and then my beta would be expected increase in life expectancy every 5 years. But I'm going to just go ahead and turn 1952 into 0, 1957 into 1 to make that beta a little easier to think about. No, it's gonna the inferences would be indistinguishable, right? If I didn't do this, my beta would look as if it were 0 when in fact there was a positive slope there. I would see it in my posterior inference, but if I was just looking at the table of parameters, I wouldn't see it.
Okay.
It would look like 0 when in fact it is positive, but it'd be really small, right? Because if we think about like 0.0001 times 1957. Right, is non-zero. But 0.3 times 1 is going to be equal to roughly, 1957 times 0.000, whatever, right?
Mm.
So I'm just kind of centering it to make the interpretation a little easier. It's an optional step, but that's what I did. I subtracted the minimum value of year from each value of year. Minimum is 1952, and divided it by 5 because that's how far apart the intervals are from each other.
Okay. So just to clarify then, all of these are sort of optional steps, but they're to scale it so it's more interpretable.
Yeah, and also to make the priors easier. The real reason here is that with a beta so close to 0, I would need a really narrow prior to allow for the sampler to work well.
Okay.
So, if I have, a positive relationship that's really close to 0, like I need like a normal 0 with like a standard deviation of like a 0.1 or something like that to get to basically give reasonable starting values to sample out the posterior. And it turns out that I'd rather just put it on a scale that's easier to think about a prior for.
Okay.
Same thing with life expectancy. Putting it at 0 and giving it a standard deviation mean, or dividing it by a standard deviation scale, just makes setting that prior a lot easier. And once we get to the complex space of the multi-level models, anything we can do to make the sampler's job easier and to make setting our prior easier is a good idea.
Okay, thank you.
I will let you all know, and I'm going to show you a bad model at the end here, but I had challenges fitting some of these models, right? These are not models that were in the book. These were kind of examples that I thought would be useful and the kinds of things I do in my research. And I struggled a bit with getting the models to converge. And so these are priors and specifications I settled on that kind of fit my intuition about how to make the sampler work effectively, and they did work. I'll show you an example at the end where I fit a model that performed really terribly with MCMC and did not converge, and I'll show you what that looks like. Okay, so all this data transformation is really just to make the MCMC engine work better and to make it a little easier on us to think about priors. Okay. So, any other questions? Okay, so here's estimating the model, right? I guess I could have just gone to the next slide to show you the code instead of going to R, but there it is, right? That's all the transformation code. And then fitting the model is really similar to what we did last time, right? We're going to have an intercept for a country, a beta for our linear time trend times the centered year variable, and right, our alpha, our intercepts for the country are now going to have a normal distribution with a mean 0, but with a standard deviation that we're going to estimate with a hyperparameter, sigma alpha. Because I centered it, I don't really need to estimate alpha bar, right? Because I know alpha bar is going to be 0. I've defined it as such, right? So I could still estimate it, but it's going to come out as 0. So I can just leave it there. That's fine. There's my prior for beta. My prior for sigma, alpha, and sigma are going to be identical, right? So I have two variance parameters, sigma, which is determining the average or the average distance of any individual observation. But remember, our observations have in them the country intercept and the linear time trend. So that's the expected difference from the country average accounting for change over time, right? So the sigma becomes our within country difference, and sigma alpha becomes our between country difference. And this is something we don't get in a typical regression model that's really cool. So here is our posterior, right? We have OK values on R hat and effective sample size. Notice I didn't actually crank up the iterations here. On some of these, if you see chains, if you get warnings about effective sample size, increasing the iterations argument can really help. And that's ITER. You could add ITER. The default is 1,000. You could increase it to like 4,000 or 10,000. And if your model still has trouble there, then you have a bigger problem. But that can solve a lot of your problems. These chains look fine, right? They're mixing well. They're exploring kind of all over the parameter space, which is what we want to see. They're not kind of trailing off in individual directions. I don't think I've shown you a bad trace plot, and I'll show you a bad trace plot today. So you can just know what it looks like. But checking your trace plots and checking your convergence is really important for these kinds of models because you can end up with bad inferences and the algorithm can fail you. Usually it'll warn you. But so here's the within and between cluster variance, right? And this is a new thing that we get with the multi-level model. So I want to just look at the posterior values for sigma and sigma alpha, sigma sub alpha, right? So the pink value here is sigma. That's our posterior for where sigma is, right? And we saw that here, right? Our beta, we're seeing, yeah, there's a 0.12 increase in life expectancy for every unit change in time, right? So as time goes up, life expectancy goes up. Our posterior for sigma alpha is centered at 1, right? And we have a pretty narrow interval there. Our posterior for sigma is centered around 0.27, and we have a really narrow interval there. So crudely speaking, we would say our within cluster standard deviation is about 0.27, and our between cluster standard deviation is near 1.1, right? So our between cluster standard deviation is higher than our within cluster standard deviation. And that's what this looks like, right? The blue is sigma alpha, the pink is sigma. So what this is saying is that the variance in our intercepts, the variance in our alphas, is higher than the variance in our individual observations, right? And remember that our likelihood is now accounting for those variations across clusters already and accounting for variation across time. So once we've accounted for those two things, we don't see a lot of differences within countries, right? Country differences tend to be pretty small, but cross-country differences tend to be very large, right? So this is telling us a lot about our data, that most of the variance in life expectancy is variance across countries. It's not variance within countries, right? We're not seeing big changes in countries over time. We're seeing relatively small changes in countries over time, but very large differences in across countries, right? So
Frank?
between and a within variance estimate. Yeah.
So you're saying this is difference between countries over time, which means different countries are seeing very different changes in life expectancy over time?
No, this model says they're not, right? Because effectively, our sigma parameter is now the within country variance, right? So we are asking how different are countries once we've accounted for that, increasing linear time trend that we see globally, right? We only estimated one line for the whole world, and we've estimated the average value for that country over time. Once we have those two pieces of information, individual countries are not that different, right? So a country in 1952 is not very different from a country in 2012 once we've accounted for that global increase and the average value of that country over time. So we're saying we are not seeing very much change in countries over time.
But we are seeing over time a lot of change between countries.
Well, so that's not necessarily over time, but that's saying those average values across countries. That's alpha, right? Sigma alpha controls the variation in our country intercepts. And those are fixed. Those don't vary over time, right? So each country gets one intercept. And that's proportional to its empirical mean, right? Times the global average times the prior. Now, so each country gets one of those. They don't get, 12 of those. So the sigma alpha tells us how different those country averages are from each other. And sigma without a subscript tells us how different individual observations within a country are from each other. Beta tells us how much change we see over time globally, right? And so sigma is kind of extra variation within a country that's not driven by this kind of monotonic global increase we see and is not driven by idiosyncratic differences of the country itself. So what sigma tells us is like how much extra life expectancy change do we see within countries after we've accounted for these other things? And the answer is some, but not a ton, right? 0.27 is not 0, but it's not dramatic. And beta is saying, yeah, life expectancy is definitely going up over time, right? The posterior for beta is really narrow, 0.12 to 0.13. That's a really narrow posterior for beta. We definitely have an increasing life expectancy over time. Once we've accounted for that 0.13 per unit time increase and whatever the average value of that country is, we don't see a lot of extra variation. You could think of that sigma as the residual, right? But another way I like, once we're in the multi-level model framework, I like to think of that as the within country variance, net everything else in the model.
So can we, can you hear me?
Yeah.
Um, I guess I'm just sort of confused as to, because we saw the plotted time before, and like it was clear that everything was very linear. So is our models taking that information, and that's what we see in the first output, the beta, right?
That's beta. This is beta, right? So this slope here is going to be really similar to what we estimate in the model. But in addition to that beta, now we're going to estimate an alpha bar for each country that's going to push above or below this line in various ways. And the distribution of those alpha intercepts is our sigma alpha, right? That's how different those intercepts are from each other is our sigma. That's going to move those around. And then the actual difference of that individual observation from the intercept plus the slope for each country is going to be that remaining sigma, right? The not sigma alpha. And so that's the kind of difference within the country that isn't explained for by that increase over time or by that, cross period intercept. So that intercept controls kind of the level that the country's at, whether it's up here or down here for all periods, adjusted by this time slope. And of course, there's differences that are not accounted for by those two things, and those differences are accounted for by sigma. And that's kind of extra within cluster difference that we could think of as driven by things like war, right? Or driven by things like pandemics, or is driven by, maybe you had you're Sweden and you discovered oil and you dramatically improved access to sanitation and healthcare or something like that. Right?
I guess my other question is that just because I'm still grappling with the priors and how they relate to each other and the model, is that just assumed in our priors, or did we explicitly state that?
That's assumed in our model.
Okay.
Right?
Because it could be, and this is, I'm sure, getting more complex. Maybe you have an example of this in the next class or so, but like it could be that there is not a linear trend in death rates over time, and then you could potentially model that or create a prior for that.
Yeah, for sure. A linear time trend is, in this case, reasonable because we, checked it out and it's increasing over time. But there's going to be a cap to that, right? Like life expectancy can't go much higher than like 80. And so there should be some nonlinearity to that. Often, time is funky a lot of times, right? And adding a line to time is usually not the greatest idea. In this case, it works. But if we were looking at like GDP, that might not work.
Right.
And we might want to estimate lines for every country, right? Or we might want to estimate lines for continents, right? And we could do that. We could definitely do that. It's a lot of complexity. We could estimate what's called, we talked about splines a little bit, right? We could estimate splines within countries or splines within continents. We could estimate quadratics or cubics or whatever, right? We could go crazy with this. A lot of times in these time series models, you'll see autocorrelation models where it's like, okay, we're going to predict out the next value based only on the prior value or the prior two values or something like that. So yeah, the line is an assumption of our model, and the intercept
that's not that's not like explicit in a prior.
It's explicit in our likelihood.
Okay.
Right? We could specify a different likelihood.
Okay.
This is
along the same lines. I had a question. So is this like averaging over year, or like I'm just trying to think in my mind, like if I were to see the exact numbers, like for example, Afghanistan 1957, Sweden 1957, Afghanistan 1958, Sweden 1958. I mean, is that kind of? I was just wondering if like subsetting by year, or is that? I don't know if I'm.
So what the beta is going to do in this context is take the average increase in life expectancy across all data points, net those country intercepts, right? So it's going to use the full data to estimate that.
Okay, that's what I was wondering.
That's a global average increase in life expectancy after accounting for the average values in each country.
Okay.
Which is a little funky to say, but yeah, it's going to be pretty close to the global line that I showed you a moment ago. It's going to be pretty close to this line.
Okay. Yes, that's what I was thinking. Right.
Yeah.
Mm-hmm.
It's not going to be exactly equal to that because we are going to account for those country intercepts, but it's going to be, we estimated a 0.14 slope per unit. I mean, and that looks like a 0.14 or a 0.2 slope, right?
Mm-hmm.
It's eyeballing it to me. So that's pretty close. But yeah, it's going to be a global slope. We're only estimating one time trend. We could do that differently. The model I'm going to show you that failed is one where I tried to estimate intercepts for a year. A good way to make the year trend nonlinear is to basically say, treat them as categorical differences and just let the average value for each year have its own intercept to let it just jump around, right? And that model failed spectacularly when I tried to estimate it. So I'll show you what that looks like in a bit. And I think it might have something to do with the priors on the model and not getting across the parameter space well, but I didn't. I kind of stopped at a certain point. Anyway, there's how we estimate the model. There's the posterior. There is our within and between cluster variance. Is everyone clear on how this within and between cluster standard deviation terms work? Because this is really a new thing. And I think it's one of the powerful things we get from multi-level models that we don't get from classical models. Okay, I'll assume that we're good then. So sigma alpha is our between cluster variation. Sigma is our within cluster variation. Net everything else in the model, right? How much variation is there within countries? How much variation is there between countries? And we see here that most of the differences in life expectancy globally are driven by between country differences, right? Okay, so what if we want to add, sorry, typo there. What if we want to add more than one cluster variable? So we know that countries are nested within continents, right? So maybe this big variation across countries is in part a function of differences across continents, right? It might be, when we looked earlier at the densities of the data, we did see that African nations tended to have much lower life expectancy than countries in the Americas, right? So it could be that differences in continents that are driven by things that we're not observing, like the political relationships between Africa and the rest of the world over 500 years, right, are driving life expectancy downward in the continent and that are pushing it upward other places. So maybe those country differences could be in part accounted for by continent differences. So we're going to add a second intercept. We're going to estimate here our alpha for country again, but now we're going to add a gamma for continent, right? And we're going to use the same prior setup that we use for our alphas. We're just going to add an additional layer of complexity to it. We're going to add this extra random intercept or varying intercept. So we're going to estimate, because we've centered our data, again, my prior is that the continent intercepts and the country intercepts are both going to be centered at 0, right? But we're going to let the sigma terms have a lot of variance. So we're fixing the center of those distributions at 0, right? Which for the continent might be a mistake. Maybe we want to let the center of the continent distribution move around a little bit, but we're going to go ahead and fix it at 0. And so now what we've got in our model is the within country variance, the between country variance, and the between continent variance. So now our within country variance is after we account for differences across continents, right? So now we're going to get a better sense of variance across continents, across countries, and within countries over time, again, with our linear time trend. Now, this is adding a lot of parameters to the model, right? But given what we've already done, this flows pretty reasonably from what we've already set up. And this is the kind of thing that you cannot do with a no pooling model, right? Once we've estimated those country averages, we can't add higher level predictors into the model, right? We can only add time varying within country predictors to the model. We can't add something as a predictor that doesn't vary. You don't have enough degrees of freedom to do that. But with the multi-level approach, we're not confined to having a number of parameters that's less than n-1 observations, right? We can actually have more parameters in our model than we have observations in the data. That's really common in a multi-level model. Okay, so,
Uh,
yeah.
so just to clarify, so a complete pooling is because it has no, like it just has one global, and so we could add other parameters to that model and have more priors, but that it would still be complete pooling if we had more priors, as long as those variables were within like that unit of analysis.
Yeah, so there's no reason we couldn't have like a global intercept for life expectancy and then add things like the country's observation of GDP to help us understand its life expectancy, right? We would call
Right.
that a complete pooling model because we haven't estimated intercepts for each cluster, right? Where
Okay,
we
cool.
really pulled those clusters apart. There's no reason we can't use unit level observations though in a complete pooling model.
Mm-hmm.
And we can get pretty good inferences a lot of times by doing that, right?
Mm-hmm.
But if we think there are like repeat observations of the same unit over time, like we've got here, there's going to be something that's unobserved about that country that's going to push it in one direction or another. Like, did they have a war? Did they have access to high quality sanitation? Right? All of those things. Did they have access to reproductive health care? Right? All of these things have dramatic impacts on life expectancy. And so those are not in our data, and so they can't be in our model, but they are going to drive life expectancy. And these intercepts are going to help us model the unobserved stuff that explains heterogeneity across clusters.
Okay.
They're going to kind of bundle up all that unexplained variation. Yeah. But yeah, we can add, plenty to this, right? So in this case, we have two parameters, beta and sigma, right? And two hyperparameters, sigma alpha for our country intercepts and sigma gamma for our continent intercepts. All right. In this case, I did crank up my iterations to 10,000 because the model was having trouble getting enough effective samples for each intercept. So I went ahead and let the model run longer, and it did converge when I did that, right? It could be that the starting values were kind of off and it wasn't exploring the space very well. If you get those, ineffective or RHAT value warnings, then increasing iterations is a good way to start. 10,000 worked for me. It just means your model's going to run a little longer. The specification here, right, is gamma continent plus alpha country plus beta times year C. As we used before, the only addition is this gamma continent, which I'm going to add the intercept distribution here, right? So the intercepts are distributed normally, and then the prior for the hyperparameter here, right? So I have two hyperparameters. Because I centered the data, I don't need to worry about adding additional hyperparameters for the center of that distribution because I've, artificially fixed it at 0. And you'll see this a lot in multi-level modeling. LME4, the package that is widely used for frequentist multi-level models in R, constrains intercepts to be centered at 0 just to make the estimation easier. So there's no real cost to doing this. Okay, now here is what the posterior looks like. It's going to take a second for my slide to render all these graphs. Right, the beta is similar to what we saw before. Our sigma alpha went way down, right? Our sigma alpha before was like 1.3, and now it's 0.5, right? So what we're seeing at the same time is the sigma gamma is 0.9. So a lot of that within country difference that we saw earlier, or between country difference, is actually explained by between continent differences, right? So once we account for the continent that a country is on, we reduce the level of variance that's explained by differences across countries. Our within country difference stays about the same, right? So there's clearly variation that's explained by differences across continents. So it's helpful to include that in the model, right? A good way to gut check whether you should have a varying intercept in your model is to look at these sigma parameters. If the sigma is close to 0, if there's not much variance explained by the intercept you've added, then it's not contributing to your model, and you can probably safely leave it out. But if you see a sigma that's, a 0.2, a 0.5, a 0.9, or higher than that, then it's explaining something that's going on. It's saying that there's variance in the data that's accounted for by this cluster, and you should leave it in the model, right? Again, any questions about what we have done here? Note that we do have a pretty wide interval on this, though, right? It goes from 0.5 to 1.5. So the continent intercepts are, very different from each other, and we don't have a lot of certainty about where they are, and that's because we've only got 5 continent categories in the data, right? So we don't have a lot of information to estimate precisely where that continent intercept is going to be. So it's pretty wide, but our effective sample size is fine, and our R hat is fine. So I'm confident that this posterior is usable and accurate for our model, but it is a pretty wide interval relative to our country variance interval, pretty narrow, and our within unit variance interval is pretty narrow. I'm sorry, this one. Okay, no questions on that?
So I assume this kind of goes back to the question I asked earlier. You could change that sigma to, like, obviously restructuring the model, but sigma year, like,
Yeah, sure. I'll
yeah,
do that.
or sigma country, for that matter.
Well, sigma country is A.
Oh, okay. Yeah, there
Sigma
it is. Yeah.
continent is G, and this is the effectively within unit, right? Or
Mhm.
within country. So we have between. We're always going to have the between or the within country in a normal model, right? Because we have a residual term. We have an error term. But that's the within country. That's the between country, between continent, within country. Now, what happens if I try and do what Anthony suggests and estimate a year intercept, right? So instead of treating year as a line, what if I treat it as an intercept where each year globally moves up and down based on the trend? Oh, rather, before we get there, let's just compare the continent model to the country-only model, right? With a WAIC score, and you can see here we get some boost in predictive performance. The weight is not exactly equal to 1 here, right? Because the difference in WAIC is 2.8 with a standard error of 3. So, the model appears to have fit better, but we're not really confident that one is a superior fit to the other. Even though we do see that this gamma parameter is explaining a lot of variance, right? So, I would stick with the continent specification just because that sigma is relatively high, but in terms of predictive performance, it's not a huge gain. Now, here's a bad model. I'm going to add a gamma for year, right, instead of gamma for continent. So now for each of the 12 years that we have data recorded, they're each going to get a global intercept. So we're going to get an intercept for a country and an intercept for years. And here I didn't center the data, right? So I have these priors that are at the 5515 again, with the really broad exponential priors for my hyperparameter, my variance parameters. And this model is bad. You can see my ineffective is 2 when I drew, 4,000 samples, right? For my alpha bar and my gamma bar parameter. It's now really uncertain where those averages are for countries. And the R hats should be close to 1, and they are very far away from 1. Right? It looks like I did an okay job with my sigma parameters, right? My effective sample sizes and my R hats aren't terrible there, but for the centers of these distributions, they were awful. So let's look at what a bad chain looks like. I don't know that I've shown you these before, but remember what our chains, typically what we want to see is them kind of with a concentration of mass about the center, and we want to see the chains exploring the same space. And here what we can see is the chains drift into wherever they want to go, and then just stay there. And each of the chains is in a different probability space, which means they're not mixing, which means each chain is going to give me different samples from different zones of posterior probability, and they're not going to be reliable for making inferences about where the posterior distribution is. So if you see chains with patterns like this, be afraid, and your model is unreliable, right? If you see the chains kind of moving off in discrete directions, and the chains are not overlapping each other, then it means your estimates are unreliable, right? And you can see here I have an effective sample size of 2, despite the fact that I drew 1,000 samples, right? It means the model is telling me you only have effectively 2 data points that you can estimate the posterior from based on this, which is not enough to make any kind of inference. So this is looking at your trace plots is really critical, right? In this case, I got warnings from my ineffective and R hat that the model probably wasn't very good. But then looking at the trace plot, I can see these are horrible, right? They're not mixing, and they are almost certainly not going to give me valid inferences for my posterior, right? What I want to see is this, where all of the lines are overlapping each other. Sorry, this takes a second to render, right? Each of the colors represents a different chain, and you can see they're all stacked on top of each other, and they're bouncing around a lot. And I have an effective sample size of 800 for this parameter and 4,000 for this parameter, right? So they're mixing really well. They're exploring the sample space really well, the posterior sample space really well. These are reliable, whereas, the others are decidedly unreliable. So that's a pathological chain. So if you see this, do not use that model, right? Reparameterize it. Think about what's going on. In this case, I have my priors are too broad, and it might be the case that it's very difficult for the model to estimate that as an intercept term rather than as a slope term, because it's hard to find information about where it should be. Okay, so to conclude, multi-level models are super flexible and super useful for modeling. Again, they should be your default if you have any kind of clustering to your data, right? Unless you have strong motivation for another approach, you should always have to explain why you didn't use a multi-level model rather than why you will use a multi-level model. They should be the default. Sometimes you'll have to convince reviewers and people who had different training of this approach, particularly people that are more on the sort of econometric side of things, and a kind of econometric approach to causal inference, tend not to use multi-level models because they don't fit as neatly into yielding clear causal identification. But the multi-level approach would say you're being overconfident in your data, and that this approach, you're overfitting your data when you use these kinds of fixed effects approaches, and that this is going to give you more conservative estimates that may not meet the criteria for strict identification, but are effectively doing the same thing, but will avoid the overfitting that you get in those other approaches. So when we have repeat observations of units over time, when we have data with clusters, we want to use a multi-level model. Multi-level models have these benefits, right? They shrink estimates toward the group means, just like the priors do, right? The priors shrink our estimates toward the prior. The multi-level model shrinks estimates toward the group means. And that helps us avoid overfitting, and it helps improve predictive accuracy. They give us those variance estimates across and within clusters that can be incredibly valuable, and sometimes are the source of what we're after. Sometimes we want those variance parameters to answer a research question, and the multi-level model gives it to us. And they also allow for flexible posterior inference, right? They allow for a really flexible approach to posterior simulation that we'll kind of get into as we go forward. So for homework, hi, Dorothy. Dorothy wants to say hi, everybody.
Hi, Dorothy. How are you?
Hi, Dorothy.
My Pokemon classes today.
For Pokemon classes today, y'all. So that's very exciting. Okay, so for homework, do the easy questions in chapter 13 and the hard 2 in chapter 13. If you've got it in you to tackle one of the hard questions. This is something that, with practice will get easier. So yeah, any kind of final questions before we shut it down for the day?
So in that final model, when you included year, obviously it was just bad. So to make if you were building your research question is what explains the variance in life expectancy in the information that's provided, the conclusion would be it's based off continent, not necessarily year or.
No, that wouldn't be the conclusion, right?
Okay.
Because my model said here that it is based on year, right? That's my beta year term. It says it's linear, but I could try other specifications for that. It says it's between countries and between continents, and that there's some variation within countries too. So I've said basically that most of the variation is variation across places once we account for the global increase in life expectancy over time that's due to things like increasing access to sanitation and the development of vaccines for infectious diseases and antibiotics and all these other things, right? But after we account for that, we still have tremendous differences across countries and across continents, right? So what I would say this shows is that there's a lot of inequality in life expectancy driven by where you live. There has been an increase over time, but even after we explain that increase over time, that's largely due to technology, right? we still see big inequalities across countries. So this was far from definitive in terms of explaining life expectancy, but it shows that both continent and country differences are bigger than within country differences. So, I would be a little cautious in terms of how I interpreted that, but that's the kind of way I would interpret something like that. Other questions? No? Okay, well, yep, the homework solutions for the last two homeworks are up now. Again, apologies for the delay on that. And post any questions on the Slack that you've got as you work through this one. Next week, we're going to start talking about multi-level models that include parameters for slopes, right? So today we talked about intercepts, but there's no reason we can't add slope terms where we have varying slopes, not only varying intercepts. And we can have a lot more complexity to these than what we've discussed today. Okay, well, be well, and I will talk to you all next